And we're back in my garage. So today we're going to continue our Furnace Basics series. This is part 4. We've been going through the sequence of operation and how those parts are tested, how they work, and so on. And today we're going to finish up with the flame sensor or the flame rod. And we're also going to go over the blower motor and how that all functions together. We'll also be going over the safety circuit, which consists of the rollouts and the high limit. So anyway, here we go. Okay, so we're going to start with our flame rod. This is also known as a flame sensor. And the job of this guy is basically to verify proper ignition of our burners. So generally what's going to happen is your hot surface igniter or your spark igniter is going to be on, and then your gas valve will open. You'll get ignition. It'll run all the way to the very end. And this is where your flame sensor will be. It'll detect the flame. It's going to send a signal to the control board saying, yeah, there's flame, and it's going to go ahead and continue its process and continue to heat. Now, if for some reason this doesn't detect that flame, and we'll get into the reasons why that can happen, it's going to first cut off the gas valve, and then it's going to restart the cycle. It usually, depending on the manufacturer, they're going to try 3 more times. If it fails, it'll usually go into a lockout. And it'll give you some kind of code, something similar to, ignition failure or something like that. Depending on the manufacturer, they're worded differently, but basically it's going to say you had an ignition failure of some sort. But that's pretty much what this guy does. It looks pretty simple. It's just a stainless steel rod, but we're going to go into the science behind it because there's quite a bit of stuff that goes on with this thing. You wouldn't think about it just looking at it because it's literally just a rod with, a ceramic insulator and a little spade. Okay, so we're going to talk a little bit about how this works. So it uses a process called flame rectification or voltage rectifying. And the official definition of that is flame rectification is a phenomenon at which a flame can act as an electrical rectifier. The effect is commonly described as being caused by the greater mobility of electrons relative that of positive ions within the flame and the asymmetric nature of the electrodes used to detect the phenomenon. Okay, so whoa, that's a crazy definition, but we're going to break it down, make it a little bit more simple. So basically, if we break it down, what's happening is you're putting AC voltage through this rod. Generally speaking, it's going to be about 40 to 80 volts AC moving into the flame. Now, the flame has a bunch of carbon molecules flying around in there. Okay. Now, what happens is that's actually a conductor within the flame. Okay. So as we're putting this electricity into that flame, it's using that as a conductor. Now, it's not a consistent conductor because it's all bouncing around. So it ends up chopping up the energy flow through there. So with alternating current, we usually have a sine wave, just like that. So I'm going to flash up a sine wave. So there's a sine wave. Now, when we have a DC voltage, it's little pulses. So now because we don't have that power flowing through there consistently, it's going to chop it up. So it's going to rectify that AC voltage into a DC. Now, because you have all those particles and stuff flying around inside the flame, that process will actually turn into a load. So the flame actually turns into an electrical load. So what that means is you're producing amperage, right? So it's not just voltage moving in there, it's amperage or current. Now, what happens is because it's been chopped up, it's basically like a fake DC energy going through there, or DC amperage. Now, what we use to measure this is microamps DC. So as that has been rectified, it's hitting the burners on the other side, and this guy is pretty much energized. Now, usually, most manufacturers will have a ground, which is right here. And this is an independent ground, an isolated ground that runs directly to the circuit board. So that microamp DC will travel through the burner assembly into this wire, run up into your control board, and your control board is going to detect that microamp DC signal. If it detects that microamp DC signal, then it means, yeah, there's flame, so it's going to go ahead and continue to run. If for some reason it doesn't detect that, or the signal is too weak, it's going to think that there's no fire. So it's going to cut off the gas valve, because you don't want to just keep the gas running if it doesn't light. There's no point to it. And you just don't want this whole thing filling up with gas, unburned gas. So that's what this does, and that's how it does it. So, and you'll notice that on most systems that have a flame sensor or a flame rod, they always have a dedicated ground attached somewhere near or on the actual burner assembly. But anyway, that's how it works. Flame rectification, you take your AC voltage, you put it into the flame, it converts it to microamps DC. The microamps DC run through this little ground wire into the circuit board. Circuit board detects that. Now, generally speaking, most manufacturers, and it varies, they require a minimum of 1.7 microamps DC to detect flame, and that can go all the way up to 10. At least that's what I've seen. So generally, a good spot is about 3. But if it falls below that threshold, depending on the manufacturer, it will consider that there's no flame there. So I'm going to go over what can cause that. But first of all, I'm going to show you a few things. So we're going to show you how to test the microamps DC, and then I'm also going to show you how to test the AC voltage moving through here, because sometimes the circuit board could fail where it's not sending voltage here. Now, if it's not sending voltage to this guy, then it's not going to work, period. So it's never going to detect flame. So that's one thing, and that's actually a very uncommon thing that people test for on these is the AC voltage. Because if you're not putting voltage into that flame, it's not going to rectify and it's not going to detect the flame. So anyway, let's get back to it. Okay, so we have our flame sensor. Now I have it isolated, so it's not touching anything. I got one prong on the tip of it, and then I have one on ground. Okay, so again, that's millivolts. I have it set to AC voltage, so we're going to power it up, and we should be getting some kind of voltage reading. So let's see which one this one is. So as you can see, we're getting about 45 volts of AC power moving through that guy right there. So I'm going to try not to touch it so I don't get shocked. But that's that AC power that's moving through the flame. So I'm going to go ahead and hook up the meter, and we're going to go ahead and fire this up, and I'll show you that DC voltage that's reading. Okay, so what we're going to do is we're going to take our meter, and we're going to go ahead and set it to microamps DC. So for this Fieldpiece, it's this guy here, the little UADC, and that's for microamps DC. Okay, we're going to take one prong, right? We're going to unplug the flame sensor, and we're going to go ahead and usually an alligator clip works really good. You just clip it to the spade on the back of the flame sensor. Okay, and then we're going to take our other wire and we're going to plug it into the wire. So we're putting our meter in series of the flame rod. Okay, now remember, my meter never shows 0. That's just how it is. It's an HS36, so it never shows 0. But we should be getting at least 1.7 or higher. So anyway, I'm going to go ahead and call for heat. And then once it's heated up enough, we're going to go ahead and have our gas valve open. So we have ignition, and now our flame sensor is detecting the flame. So it's putting in that 45 volts AC into the flame. That voltage is reacting with the carbon molecules inside the flame, and it's chopping it up and converting it into DC amperage, which is running back through that ground and then into our circuit board, telling the board there's flame. And so it's going to continue to run. And then once it runs for a little bit, our blower motor will come back on. Now, as you can see, we're getting 2.7 microamps DC from our flame sensor. Now, when you're testing this, you want to make sure it's above the threshold. So generally speaking, you want it to be about above 1.7. Okay? Now, if for some reason this is unplugged, it's going to go out. It's going to cut the gas valve off. And the reason being is because it's not receiving voltage. Okay? So it's not receiving voltage, so it's not able to rectify that AC voltage into DC microamps, and the flame sensor's not, or I'm sorry, the circuit board is not detecting that flame. So you want to make sure all your wires are plugged in all the way. If for some reason it does this, so if inducer comes on, pressure switch closes, igniter comes on, gas valve, you'll see it do this. So I'm going to go ahead and cycle it. with the flame sensor unplugged. So we get our inducer, our pressure switch is closing, we get our hot surface igniter, and there it goes. And now we're going to get gas valve. So this is what happens if the flame sensor is not detecting flame, okay? So gas valve is going to open. 1, 2, 3, 4. So it has 4 seconds to detect flame, but as you can see, it cut off after 4 seconds, and that's because it didn't detect the flame. Now in this case, it's because it's unplugged. So it's not rectifying, so there's no signal for the circuit board to detect. Okay, so what other causes could it be? Obviously, we check the voltage, the AC voltage. We want to make sure we're getting AC voltage from the control board to that flame sensor. If that's not happening, well, then there's probably something up with the board. We want to make sure everything's plugged in. Now, another thing that can happen is we can have this all plugged in, but our ground could be bad. So this guy right here, I'm going to go ahead and unscrew it. Okay, so we've disconnected the ground from the burner assembly. And so that means that there's no path to the circuit board for the unit to detect the flame. So I'm going to go ahead and cycle it on, and this is what's going to happen. So you want to make sure that all your grounds are connected. And again, it could be a system that has multiple grounds. It can actually run from a standard ground into the board. Some of them it's, you know, specific, but anyway, we got our igniter coming on, and we should have our, and as you can see, we have no reading from the meter, and there it goes. So yeah, so that's because there's no ground connected. So I'm going to go ahead and reconnect the ground, and then we'll start it up again. 1, 2, 3, 4. And as you can see, we're getting a reading of 2.6 microamps DC. So the system is working, okay? That's because our ground is connected. So always make sure that this wire is not nicked or unplugged, or sometimes the connection can get corroded and it's just not making good contact. So those are some things you want to look for if you have a situation where you're not able to detect flame. Now, the most common issue with it is cleaning the flame sensor, and that's because it's in the flame, so sometimes it gets some major carbon deposits on it, and it will actually act as an insulator. So basically, the rod will become insulated, and so that AC voltage is unable to touch the flame. So if that voltage is unable to touch the flame, then it's not going to be able to rectify it. So one of the most common failures with these guys is pretty much it's just dirty. Now this one's actually a little dirty. So what you want to do to clean these is, a lot of people will use sandpaper. I used to be someone who used sandpaper, but the problem with the sandpaper is you actually end up scratching the surface. And it basically just becomes porous, and it'll just get dirty like real quick. So it actually makes it get dirty faster. So I usually use this now, which is like a Brillo pad type material, and you just want to take it like that, or you can use a dollar bill. But yeah, so anyway, you can go ahead and clean it just like this. And one of the situations I've come across in the field with these flame sensors, and this is actually something a lot of technicians miss. So you get a call for no heat. You get to the customers, they say, yeah, I turn it on, it heats the house, and then it reaches temperature and it shuts off. Then when it comes to come back on, it doesn't light up, and then it just goes off. So generally what happens is the system will light up the first time, it will detect flame, okay, because it's cold. And what will happen is, as it heats up, for some reason, it will, I don't know, solidify the junk on it, but basically it's just a dirty flame sensor. So what happens is when it's cold and it first lights, it's still sending just barely enough signal to tell the board that there's flame. But then when it goes to start up again, it's right below that threshold, and it basically says there's no flame, and then eventually it'll lock out on a failed ignition. So if you get and I've had a bunch of techs where they've been there 3 times, they fire it on, it works, and then they leave. Talk to your client, ask them, hey, does it work the first time? If they say yes, what you want to do is fire it up, let it run for 5 minutes, cycle it off, cycle it back on, and then you'll see your issue. Or you can test this, and if you see it's a really low signal, then that means, you know, it's probably just dirty. So as you can see, it's very easy to clean, and it makes a big difference. And so anyway, we're going to move on to the blower motor and how that's relative to the heating system. So My unit is just too difficult to deal with because of that big panel and the flue pipe in the way. So we're just going to go over this real quick. So after everything turns on, the last thing that's going to happen is your blower motor is going to turn on. If for some reason the blower motor doesn't turn on, it's going to overheat and it's going to set off the high limit switch. So this is very important for airflow problems. If your blower motor isn't running, it'll overheat and set off the high limit switch. So if for some reason this isn't turning on, the first thing you want to do is you want to make sure you're getting power. So on these circuit boards, there's different taps. So you have one for cooling, one for heating. If it has multiple stages, it might be high cool and low cool, and high heat and low heat. Then you have parks, and these are just the extra speed taps. So you can change the speeds if you need to. So black one right here is on cooling, that's high speed, and then this blue one is on heat, that's medium high. So the default is usually it's going to be low to heat, but if you ever, like if it's set to low and you have a big duct system, it's not enough airflow, you can switch the red one for the blue one or the orange one, which is, so that's going to be low, that's going to be medium low, that's medium high, and then that's high. So that's generally, now it depends, they can be different based on different manufacturers. So anyway, if for some reason the blower motor doesn't come on, there's a couple things you want to do to make sure. So first and foremost, you want to check the capacitor. So let's check this capacitor. Okay, so we have our meter set to MFD. This is a 12.5. So we're going to pull these wires off. And you can't check it with the wires on, it throws off your reading. So you always want to take the wires off. So put one on each. And my meter takes a while, but we are at 12.5, perfect. So if we check that out and the blower is still not coming on and your capacitor is good, now is the next step. The other thing it could be is the relay in the circuit board is not closing, so it's not sending the power to the blower motor to turn on. So there's a couple ways we can check for that. So let me get set up for that and we'll show you. Okay, so right now I'm cycling R to G, but the door switch is not engaged yet. So what we want to do is we want to check voltage between the speed tap. Now, when you're running in heat mode, it's going to use, when you call for fan, it'll use the heat tap. All right, the only time this one is used, the cool tap, is when it's cooling. So this is what we're going to check, see if we're getting voltage. So what you can do is you can pull that off just a little bit so you can get your prong in there. And we're going to go from heat to neutral. You could do to ground, but it's better to just use neutral because you don't know where that ground's going. Okay, so it's on. We have our meter set to voltage. We have one prong on neutral, and now we're going to put this one here. So we have 120 volts going to the motor, so that's good. Now, if you have 120 volts coming out of there, that means that the relay inside the circuit board is good. Now, if the blower motor is still not coming on, there's a couple things we can do, okay? Now, these motors do have a thermal overload, so if they get too hot, there's a little thermal switch in there. It pops open, it kills the power to the motor. So the power will be going to the wires, but it won't go to the windings. It kills it before it hits the windings. So a couple things you can do is you can get your laser gun or your thermal, infrared thermometer, and you can shoot the motor, see how hot it is. So our motor is only 81 degrees. Now these things, usually the thermal overload, generally speaking, depending on manufacturer, will usually be 130 to 140. So if it gets that hot, it's going to shut off. Now these things usually won't go past 100 degrees when they're running on a hot day. So if it's super crazy hot, that means you have a thermal overload. So what you want to do is kill the power, and you want to go ahead and see if you can spin it. Now this one is definitely spinning. You can see that's kind of dark in there. So if it's stuck, you want to make sure there's nothing stuck in there that's causing it to bind up. The other thing too is if there's a lot of resistance, could be bad bearings. So the next thing you want to do, you want to check your amp draw. So we're we're going to hook this up. Okay, so our amp draw is at 2.93-ish. Now keep in mind, when you put the door on, the amp draw will actually be a little bit lower because by having this door open, we're increasing the static pressure because it's pulling in a bunch more air from the return and from here. So it has to work a little bit harder. So the amp draw will actually be a little bit less when you put the door on. But this should never be more than 7 unless it's like one of those big, huge carriers, the really wide ones. Then I think they're usually 10 is the max. But you want to check your nomenclature to see, you know, the little data sheet sticker that's on there and see what the max is. But generally 7 to 10. If it's a small one like this, it's usually going to be under 7. If it's a bigger one, it's usually under 10. Now, if it's pulling crazy amps and it's not spinning, bad motor. So let me show you a quick little trick you can do to test the motor. So let's say you find that you're not getting voltage from the board, but you want to make sure that the motor is good because you don't want to change the board because sometimes both could be dead. So what you do to test it is you can actually unplug one of the speed taps, and keep in mind sometimes one speed tap might be bad, so sometimes you can switch the speed and it'll come on as a temporary fix. I still recommend replacing the motor, but if you're trying in a pinch and you're trying to get them some heat or some cooling temporarily, you can do that. But anyway, what you'll do is you'll have 2 lines going to your door switch. One's going to be going to the circuit board and one's your line coming in from the service. So you're going to unplug, kill the power first, unplug the one going to the circuit board, and then take one of the speed taps that you're trying to test from the blower motor, right? And plug it in there. So now, if we push this, if the blower motor is good, it's going to turn on. We unplug it, turns off. So that's one little trick you can do to see if the motor's working. If you think maybe there's something up with the board, this is a great way of doing it, just to make sure that the motor works. Okay, so that's pretty much how we check on this blower motor. Okay, so the safety circuit consists of a couple different things. So these right here are rollout switches. Now there's 2 types. There's self-reset and there's manual reset. So these are actually self-resets, but usually in the middle you have a little button. I'll go ahead and show you a picture of one. See, so that's what it looks like. That little thing in the middle, that's a button. So the way these things work is you basically have a disc in there. If it gets hot, it pops and opens some contacts and it cuts the power. So you should have 24 volts moving through this thing even when you're not calling for heat. So there's 24 volts moving through this constantly. If for some reason anything interrupts that voltage, it's not going to run back to the circuit board. So it runs 24 from the board through all this and then back to the board. If it doesn't detect that 24 volt signal, then that means that something was tripped, so it's going to cut off the gas and it'll probably run the fans to try to cool itself off. Now you have another safety here, and that one's in the back right there. Right there, you see that thing? That's the high limit switch. The high limit switch, that's used to measure the temperature of the air moving through the heat exchanger. If for some reason that temperature gets too hot, it's going to go ahead and trip that switch, and when it trips that switch, it's going to go ahead and cut that voltage, and the control board is going to go ahead and cut the gas off, and it's going to run the fan until it cools. So if you ever look at one of those and you see it'll say like L160-40F, that means at 160 degrees it's going to trip it, and then if it drops 40 degrees cooler than that, it's going to reset. Okay? And most of the time those are always self-reset. So if you ever get a situation where a customer tells you, my furnace runs for about 10-15 minutes and it cuts off, you probably have an issue with your high limit switch. So what can cause the high limit switch to go off? It could be a dirty filter. It could be the blower motor's not running. It could be a clogged evaporator coil if you have one. It could also be some kind of obstruction in the furnace itself. Or you could, very rarely, it could just be a bad, high limit switch. Now, generally, they go bad for a reason. They don't just randomly go bad. That means it's been tripped a couple times, because they're only designed to really get tripped maybe like 4 or 5 times. But if they're getting tripped constantly and resetting, they sometimes will get stuck and they won't reset. So if you have a situation, where it's been tripping a bunch of times. You want to find the cause, and generally speaking, you want to go ahead and replace it. Now, the way you would test for it is you just stick a thermometer in there and make sure that it's going off at the right time. So if it's set for 160 and you stick your thermometer in there and it's like at 120 and it trips, well, guess what? It's supposed to trip at 160. That means it's tripping too early, so you probably have to replace it at that point. But it's very rare that you have to replace them. Usually it's because it's been tripping constantly. And then also the rollouts, that's in case you have flame rollout, and that's where the flame runs back. So it's going to kiss these guys right here, and it's going to trip these. So generally, they actually have a button in the middle that you push to reset them. But don't just reset it and leave. You want to find out why it got tripped in the first place. It's very rare that these things just trip for no reason. So never bypass these. Never just reset it and go. Reset it, stand to the side of the furnace, and watch it and see what happens. And the reason why I say stand to the side of the furnace is that way you don't get your eyebrows burnt off. I've seen it where there's been a fireball shoot out of these things. Especially the older units, because they don't have an inducer. So sometimes the flue pipe gets clogged and you'll actually get like a flame rollout or a backdraft or something crazy. So yeah, I had one eyebrow for quite some time early in my career. So anytime I turn on a furnace for the first time that I haven't seen before, I always kind of stand to the side just in case. But anyway, so these sensors here rarely just fail on their own. If they've been tripped, there's a reason. Find that reason. It could, for these guys, it's going to be flame rollout. Also, the wires could be messed up or broken, so you want to check continuity. So if I wanted to check these guys with the power off, I can just use my continuity, and that's pretty much where you can touch the two prongs together and they beep. So the best way of doing that is what you want to do is you want to find your wire that comes into it first, right? So let's see, this wire runs through there. Okay, so the wire here is from my circuit board. So there's a couple ways you can do this. You can check each individual one like this and just go across. See, I'm getting tone, so that means it's closed. And I go here. Okay, so I have tone. Okay, so I want to check my high limit, so I'm going to go across each prong. And I got tone, so that means it is closed. Now, if for some reason it's not toning, that means it is open, and that means it's been tripped. Now, a quick way of doing this is you can see I have yellow wires going to the rollouts. What I can do is I can take my see where my connection points are at my circuit board. Now, this one's really nice because it actually tells you what goes to what. So it's going to be these two yellow wires here. And what we can do is we can actually stick our prongs right in there, right into that little hole there. Now keep in mind you want to do this with the power off. Okay, that's one. And see, we stick it in there, we have continuity. And so by doing it here, that tells us that the entire circuit, so all the wires, all the rollouts, everything is not tripped. Okay, so that's a quick way of doing it. But if you ever do that and one of them isn't reading or you're not getting that tone, that means one of them is tripped, and that's where you got to go one at a time. Now, generally, the quickest way I like to do it is what I'll do is I'll stick one of these in here. And then I'll take this one and I will go one at a time. So I'll go from there to here. I have tone, so I know that's good. Then I'll move over to the other side of the switch. That's good. Move over to the next one. That's good. Move over to there. Now let's say this wasn't beeping. That would mean that this guy's tripped. So I can check the whole circuit one at a time if I need to isolate which one's bad. And the nice thing about doing this is you're checking the wires all at the same time. So yeah. And now if you're checking this while it's under voltage, now most units, even when they're on standby, there's 24 volts going through. This particular unit doesn't do that. It only sends voltage through the safety circuit when it's calling for heat. but some of them will always have that voltage running through it, even if you're not heating. Like you could be running the air conditioner and you have voltage. But pretty much with that is if you check across them while it's live, you should show 0 volts. Okay, if you show 0 volts, that means it's good. That means it's closed. If you show 27 volts or 24 volts, that means it's tripped. So that's how you check it under power. But anyway, that's all for today for part 4. I think there might be another part. I haven't decided yet, but we're going to call this as our last episode for now for our Furnace Basics series. There will be more in the future, but probably in the future, because we might actually be getting into air conditioning pretty soon. But, well, actually not here because it's snowing. But anyway, thanks for watching. Make sure you like and subscribe. Comment. Tell me what a horrible technician I am. Hit that bell notification. And follow me on Instagram and Facebook. Thanks for watching. See you on the next one.